In previous lectures, we've looked at regression where the outcome is quantitative. In this lecture, we're going to be turning our attention to the case where the outcome of interest is a binary variable. So frequently, when we're doing analyses, we care about situations where the outcome is not necessarily quantitative. For example, it's not the revenue that you get from a particular action, or it's not the amount of time that you've spent on a particular study or anything like that. It's just a 0, 1, what's called a 0, 1 variable or a binary variable. So some examples of these are if a patient is alive or they're dead, there's no sort of in between. If there's a win or a loss for a particular sports team, success or failure, whether a particular species has died or not died, and so forth. All of these outcomes only have two values. And so linear regression, like we've seen in the previous examples where we're typically assuming that the outcome is quantitative, may have some problems, and we'll explain those in a minute. And so we're going to talk a little bit about how you can address analyses if you aren't doing sort of basic linear regression. So the example that we're going to use in light of the recent victory by the Baltimore Ravens in the Super Bowl is going to be actually some data on the Baltimore Ravens over the past year in their schedule. And so what I've actually done is collected some data from the Ravens season, and so that data is available here, and I download it and load it into R. And I have 4 different variables here. So I have, for each game, I have a numeric variable that indicates whether the Ravens won or not. It's 1 if they won and 0 if they lost. And then another variable that's W if they win and L if they lost. A Raven score variable, so that tells the score that the Ravens got in that game, and the opponent score is the number of points that the opponent scored in that particular game. And so you could imagine fitting a linear regression model where you want to say something about whether the Ravens won or not. So that's a 0 or 1 variable. Either they won or they didn't. And you can relate that to the same linear model that we had used previously is one way you could look at this. And so you could have B0 plus B1 times the score, the number of points that the Ravens scored in a game. So you'd imagine as they score more points, they're more likely to win. So it turns out that interpreting this model, you get that B0 is actually the probability of a Ravens win if they score 0 points. So if they score 0 points, you only have this term, and so we're just averaging the number of times that the Ravens won when they had scored 0 points. In this case, that was no times that they did that. And then in B1, it's the increase in probability of a Ravens win for each additional point that they score. So each time they score a point, we actually increase the probability of their win a little bit. And then E is again the variation due to everything that we didn't measure, both random variation as well as potential measurement error, things that we didn't measure about whether the game was a home game or an away game and so forth. So in R, we could fit this linear regression model just like we've done in the past. So we can take we have, again, the numeric variable that indicates whether the Ravens won or not, and then that's the outcome, and then we have the tilde, and then we have the covariate variables that are we're trying to use to explain that. And so we have here the Ravens score as our covariate. If we look at a summary of this linear model, we actually get an estimate for the probability that the Ravens win if they don't score any points, which is 0.28. So that's already indicating that there's something a little bit weird going on, right? Because you'd expect that if they scored 0 points, they'd be unlikely that they'd win. And then also they have, for every additional score that they have, they gain a probability of 0.0159 of winning that game. So if they score 10 points, then they actually increase their chance by almost 15% of winning the game. That's probably due to the Ravens' outstanding defense. So if you plot the fitted values from this linear regression, we're plotting on the x-axis here the score that the Ravens had in their games, and on the y-axis it's the probability of winning, which is the outcome in this is the estimated outcome in this linear regression. We actually see that one of the probabilities over here when they scored a lot of points is actually estimated to be greater than 1. So of course that seems that's impossible. The probability can't be greater than 1, but that shows you one of the examples of the problems that you can have when using linear regression on binary outcomes, in this case on probability or on a win or a loss variable. So we're going to be talking about ways that you can represent these probabilities other than just the outcome itself. So remember that the Ravens win variable is 0 or 1. It's called a binary outcome. We could look at the probability that the Ravens won given some variables like the score that they had, the coefficients maybe from a model and so forth. We could also look at what's called the odds, which is a way of formulating or looking at probabilities that's helpful or useful to gamblers. But it's also going to be, as we'll see in a minute, a very useful way for us to be able to model these variables ourselves. And one of the reasons why is that the probability is on interval 0 to 1. So this actually poses some mathematical problems because you have these boundaries, hard boundaries at 0 and 1, whereas the odds can be anything from 0 all the way up to infinity. In other words, it can get as big as you want. As this probability gets smaller and smaller and smaller, so as this probability gets smaller and smaller, this variable gets closer and closer to 0. As the probability gets closer and closer to 1, this denominator gets close to 0 and this thing gets very, very big. You could also take the log of this variable, and so the log of the variable actually now will take on all the values from minus infinity to infinity, and it turns out that this is not necessarily that useful for us in terms of applied research, other than the fact that the mathematics and the computation of solving equations when the outcome is on an unbounded interval like this are somewhat easier, and so that means that we'll get more stable results from our analysis. So the difference between linear and logistic regression is basically just changing what we're going to be looking at for the outcome. So in a linear regression, we wrote down this model where we had Ravens win was equal to B0 plus B1 times the Ravens score plus a term that explained all of the, or that captured all the unexplained variation. Another way of writing this down, writing this exact same model, is to say that we're going to set the expected value or the average of the Ravens win variable, the 0, 1 variable, for a specific Ravens score is equal to these terms, B0 plus B1 Ravens score I. This is actually just another way of writing this down. In other words, we're basically saying the probability of a Ravens win, this is the average of the 0, 1 variables, is equal to a specific value where that value is given by this model. In a logistic regression, we actually do it just a little bit different. What we do is we model the probability of a Ravens win. So instead of looking at the Ravens win itself, we actually look at this probability, and we model that as this function. So it's a little bit funky. We say e to the b0 plus b1 times Ravens score divided by 1 plus e of this score. And the reason why we use this funky function is actually because if you do a little algebra, what you end up with is that on the left-hand side of this equation, this is the log odds now, right? Because we have the probability on the top, 1 minus the probability on the bottom, that's the odds. We take the log of it, and it's equal to B0 plus B1 RSI, so Raven score here. So what this is it's saying that we're going to model the log odds as being a linear function. And that has some advantages, as I mentioned before, because this isn't a constrained number anymore. It can be any number from minus infinity to infinity, so we won't get those problems where we might be estimating a probability outside of 0 or 1. So the way that we interpreted this is, so we now are fitting this model as opposed to the model where we had just the expected value of the Ravens win score over here on the left-hand side. So how do we interpret this? B0 is interpreted as the log odds of a Raven win if they score 0 points. So if the Ravens score 0 points, we get the log odds is equal to B0. And B1 is what's called a log odds ratio of a win probability for each point scored. So basically what happens is for every additional point, we're comparing the log odds when you add that point to the log odds when you didn't have the point, and that's the log odds when they scored 0 points. So e to the b1 is actually just the odds ratio. So if we don't want to deal with this log anymore, we can take e to the b1 and we get the odds ratio of a win probability for each point scored. So I'm going to explain, this is obviously a little bit more complicated than just dealing with a 1 unit difference in our Raven score leads to a 1 unit difference in Ravens win. Of course, a 1 unit difference in Ravens win doesn't really make that much sense anymore, since there's only one 1 unit difference. You can only go from 0 to 1. So I'm going to explain odds. These are actually slides that I've used from a fellow professor, Ken Rice, at the University of Washington. And so here's what we're looking at here are survival data from a genetic study. So you can have one of 3 genetic markers. It doesn't matter. You don't have to know the details of what these different letters mean, but you can imagine there are 3 different markers that you can have. And so you can have then a probability of surviving. So in this case, if you have marker AA, you have a 66% chance of surviving. If you have marker big A, little a, you have a 50% chance. And if you have little a, you only have a 10% chance of surviving. So the top number here is the probability of death. So the probability that you won't survive. And then the odds of death is just the ratio of the probability that you're going to die to the probability that you're going to survive. So in this case, it's probability that you're going to die is 33%, probability that you're going to survive is 66%, and that reduces to a fraction 1 over 2. In the case of big A, little a, you have a 50% chance of dying and a 50% chance of surviving, so the odds ratio is 1 over 1, so it's just 1. And in this case, the probability of death is 90%, and the probability of surviving is 10%. So you get an odds ratio, or sorry, an odds of 9 over 1, which is 9, which is a very large odds. So we were talking about odds ratios, and so interpreting those, what does that look like? So what this is the plot of data. So now what I've done is, for a continuous variable here, I imagine that each of these white bars is the probability of surviving, and the black bar is the probability of death. So over here, you're unlikely to die, and over here, you're very likely to die if you have a value near 3. And this plot is designed such that between every 1 unit difference in x, the odds ratio is 1. So between x equals 0 and x equals 1, the odds ratio has changed by 1 unit. So you can see that this is what the curve looks like for an odds ratio of 1. It's no longer a straight linear curve, right? It kind of has this curvilinear shape to it. The odds ratio is constant, but the probability itself is declining in sort of a curvy manner. So just to give you another idea of what this looks like for different odds ratios, so imagine these are your data points. These are the blue are from one group and the red are from another group. If you fit a model that looks like this, where you have a straight line for this group and then the fitted values are these for the other group, this has an odds ratio of infinity because you have this jump right here at this point. An odds ratio of 1 actually is just a flat line. That's because the odds aren't different between either of the two groups. And then each of these curvy lines is a different odds ratio curve. So you can see that as the odds ratio gets bigger, you get something closer and closer to this odds ratio of infinity line, which is just a jump. So you can perform a logistic regression in R using the GLM command. The GLM is actually a more flexible command representing all generalized linear models, of which logistic regression is just one sub-example. So we treat this actually very similar to the way you do a linear regression in R with the LM command. You put the outcome on the left-hand side. So in this case, this is this 0, 1 variable determining or stating whether a Raven's won or not. Then a tilde, then the covariates on the right-hand side separated by plus signs. In this case, we just have the Raven score variable as a covariate. And then you tell GLM family equals binomial, which tells the GLM command to do a logistic regression. So you always set this parameter equal to family equals binomial if you're performing a logistic regression in R. Then you can look at a summary of this object, and it looks very much like the summary of the object that you would get if you did a linear regression model, but these coefficients are actually interpreted very differently. So the intercept term is the log odds of a Ravens win when they score 0 points. Since this number is negative, it actually suggests that the Ravens are less likely to win than they are when they score 0 points than they are to lose. So in other words, it's more likely they're going to lose. And then this number, the estimate for the Raven score term, is the log odds ratio for a 1 unit increase in the Raven score. So every time the Ravens score 1 point, their log odds ratio is increased by 0.1. And so what you can see is, since this is a positive number, as they score more points, they're more likely to win. And so that's not surprising. You can look at the standard errors and the z-values. These are just like, you could use them very similarly to the way that you use the same terms in a model in a linear model. And so, for example, these are the p-values. And again, you can look and see if these p-values are statistically significant, where they're less than 0.05 or they're match some threshold that you've set in advance. So to show you a little bit what it looks like, instead of fitting a line through the data, it looks a little bit different. So what I'm showing you here on the x-axis is the score, the number of points that the Ravens scored. And on the y-axis, I'm actually showing you the estimated probability that the Ravens will win, which we can calculate from this logistic regression model. And instead of seeing that straight line that we saw with the linear regression with 1 point above a probability of 1, you actually see something that's a little bit more curvilinear like this. So you can see that at first, scoring a lot of points increases their probability a lot, whereas the difference between scoring 42 points and scoring 58 points or something is a relatively small difference in their probability of winning, which may make a little bit of sense in the sense that if they run up the score, it doesn't really help their probability of winning very much, but it does change it. It gets a little bit better as they get larger. So you can actually make confidence intervals for the odds ratios, and so the odds ratio, remember the log, the logistic regression actually gives you the log odds ratio as a coefficient. So to get the odds ratio itself, you have to exponentiate that term. So log odds ratios less than 0 mean that it's more likely for the Ravens to lose. Log odds ratio greater than 0 means that it's more likely for the Ravens to win. Once you exponentiate those terms, a log odds ratio less than 1 means that the Ravens are more likely to lose, and a log odds ratio greater than 1 means that they're more likely to win. So once we exponentiate, we're looking at this term and we're trying to decide whether it's bigger than 1 or less than 1. And then we can calculate confidence intervals in the same way. We use the confidence interval function and we exponentiate those terms, and we can get confidence intervals for the log odds of for the odds of a Ravens win if they score 0 points, and then for the odds ratio for each additional point that they score. So in this case, this confidence interval covers 1. So remember, an odds ratio of 1 means that there's no difference in odds of winning as they score more points. And so since this odds ratio or this confidence interval covers 1, it means it's not clear that there's a significant relationship between the number of points that the Ravens score and their probability of winning, which could be due to a number of different variables, including things that we've left out of the model like the home field advantage or the amount of defense that the Ravens are playing. You can also perform something similar to an ANOVA for logistic regression, and you do that using the ANOVA command applied to the logistic regression object that we've created. And so what's happened here again is that the terms are added one at a time, just like we talked about with ANOVA. And in this case, instead of looking at residual sums of squares, it looks at something called the deviance residuals. This has to do with the log likelihood of the term, and we're not going to get into too much detail as that's pretty mathematically technical. But at the end of the day, you can actually calculate a p-value very similar to the p-value that you would calculate from an ANOVA table. And so what we can see here is that the Ravens score variable is very near statistical significance when we include a ANOVA model for the probability of a Ravens win. One slightly tricky thing that can occur when you're doing these sorts of examples is something called Simpson's paradox. So in this study that I'm describing here, this is actually a study of kidney stones, and so they have two different kinds of kidney stones, small kidney stones and large kidney stones, and then they have two treatment groups, treatment A and treatment B. And they look at how many people the treatment is effective for the small stones and for the large stones. So treatment A is better actually for both the small stones group and the large stones group. But once you actually add up the numerators and the denominators of these terms to get the total, you actually see that treatment B is a little bit better overall for the total group. And so can be a little bit confusing. So if you don't actually have this second variable, small stones and large stones, you would actually think that treatment B is better, whereas for each of these different subgroups, it's actually the treatment A treatment that's better. So this seems very, very confusing, and it's hard for people to get their head around when they first take a look at this. I encourage you to go and read the Wikipedia page, which is actually quite good in terms of explaining this phenomenon. But the important take-home message here is that if you ignore potential covariates like small versus large stones when you're looking at an outcome here between treatment and how well it's successful in these different groups, you can actually get the sign of or the direction of the effect in a totally different direction. So instead of saying that treatment B is better, you would say treatment A is better if you had this extra information. The key take-home message there being that when doing a logistic regression, just like when doing a linear regression or any other type of regression, it's important to consider what are all the important terms that might need to be included in your model. So an important component of this is interpreting odds ratios, and it's a little bit different than interpreting just normal effects on a linear scale, and so I thought I'd talk a little bit about that briefly before finishing up. So first of all, odds ratios are not probabilities, so they're not between 0 and 1, and they shouldn't be treated as such. Odds ratio of 1 means that there's no difference in the odds. In other words, the probability of the event happening is exactly the same in the two groups. So odds ratio of 1 means there's no effect. If we take the log of the odds ratio, that the log of 1 is 0, so a log odds ratio of 0 is, again, no difference in the odds, which means that there's no effect. So the coefficients that you actually get out from the GLM command in R are on the log odds ratio scale, so you're looking at whether that coefficient is bigger than 0 or less than 0. An odds ratio greater than 0.5, or sorry, less than 0.5 or greater than 2, in other words, if the odds are twice as big in one direction or the other, is kind of considered a moderate effect, just to kind of orient you to sort of what a normally a moderate effect is. This, of course, varies hugely by the field that you're considering. So this is more like a very vague rule of thumb just to kind of get your head around it, but you should definitely consider the problem that you're working on, what matters. The relative risk is actually something that might be easier to interpret. In other words, what's the ratio of the probability a Raven's win for different values of the Raven's score? This is easier to interpret because it's not an odds that we're doing in a ratio here. We're just doing the ratio of two probabilities. For small probabilities, the relative risk and the odds ratio may be close to each other, and so sometimes people use logistic regression to try to estimate the relative risk, but in general they are not the same thing, and they shouldn't be interpreted as the same thing. It's probably the most common misinterpretation of an odds ratio is to treat it as a relative risk. This Wikipedia article on the odds ratio actually has a lot of information about how you can interpret the two and what's the relationship between relative risks and odds ratios. So further resources, there's the Wikipedia page on logistic regression. This is a very nice introduction to logistic regression and generalized linear models in R. Brian Caffo from Hopkins has some really nice lecture notes on Simpson's paradox and case control studies, which is one place where 0-1 data come up a lot. And then the free open intro textbook actually has a very nice chapter on logistic regression.